Alright, today in this lecture we are going to summarize some set theory. First of all, what is a set? Set is a collection or assembly of objects called objects that are distinguishable. Okay. Collection of distinguishable objects. For example, we write a set like this. 1, 2, 3. So this is a set of 3 objects that are numbers 1, 2, and 3. And obviously, in a normal sense, we can distinguish between 1 and 2, 1 and 3, and 3, 2 and 3, and so on, right? So this is a set. And this is not a set. Okay. Because this one and this one, they are not distinguishable. So this is not a set. So this is a set, not a set. Technically, this is called a multiset. Okay. Actually, multisets are important in the theory of databases, but in usual mathematics, we do not deal with multiset mostly. Okay. Next, the cardinality. We define this term cardinality, which means basically the number of elements in a set. Okay. Suppose we have a set A, which consists of n elements, A1, A2, An. Then the cardinality of this set is denoted by this. It's like absolute value or modulus. Then in this case, since there are n elements, the cardinality is n. So this is a case for a finite set. There are a finite number of elements. And if the number of elements is infinite, then the cardinality is infinite. But there are many kinds of infinities. So infinity is not a number, so be careful. And one special set is this. It's an empty set. Actually, the empty set is unique. So we say not an empty set, but it's the empty set. Okay. This is the set that contains nothing. Okay, so empty set is denoted as this, for example. So since there are no elements in this set, its cardinality is 0. And one easy way to define a set is like this. Just enumerate all the elements within the set. So that's one way to define a set. But another way to define a set is to specify a property that is satisfied by the elements of a set. For example, let's say P is a property. Then we can define a set, say A, set of X. X it has property P. Okay, but what is a property? Maybe it's easy to see by a concrete example. For example, suppose we have a set like this: 1, 4, 9, 16, and so on. So what is this set? This is a set of perfect squares of natural numbers. So we can write 1 is 1 squared, 4 is 2 squared, 9 is 3 squared, and 4 squared are squared, and so on. So instead of enumerating like this, we can write this set A as set X, and it's a set of X, and X is a square of a natural number. Or we can write X, and X is the square of n, where n belongs to the set of natural numbers. So this one here, this part, is the property we are talking about in this case. So in this case, the property is x is a square of some natural number. So that's a property. So if x satisfies this equation with some natural number, then x is an element of this set A. And another example is, let's say, set of x where x is less than 0 and x is greater than 1. Okay, obviously this set is actually empty because no number satisfies this and this. No number is less than 0 and at the same time as greater than 1. So this set must be empty. Okay, if this and is replaced with or, then there are infinitely many elements in this set. So the cardinality will be infinity. Next, if A is a set and X is an element of A, which means X is one of the members of this set A. In this case, we write X is an element of A, like this. And if X is not an element, then we write X is not an element of A. So X is an element of A. So this is the complement or negation of this. X is not an element of A. Next, we define the notion of a subset. Let's say A and B are both sets. Okay. Then, let's say, if all the elements of A is included in B, then we say A is a subset of B. More formally, we say if for all elements of X belongs to, for all elements of X, this X is also an element of B. Then A is a subset of B. And we write A is a subset of B. Or we can also write like this. So with a bar here. So if A and B are the same set, then still A is a subset of B according to this definition, right? Because A and B are the same. If A and B are the same set, then every element of A belongs to B. Okay. And if A is a subset of B, but they are not equal. A is not equal to B. Then we write like this. Okay? If A is not a subset of B, we write like this. Okay? And also, if A is a subset of B and B is a subset of A, then this means these two sets are equal, and we write like this. So this means every element of A belongs to B and every element of B belongs to A. So if both are satisfied at the same time, then these sets must be equal. So that's what we mean by the equality between two sets. Okay, let's see an example. Suppose A is a set of A and C, and B is a set of A, B, C, D. Then A belongs to this lowercase a belongs to this set B, and lowercase c belongs to this set B. Therefore, A is a subset of B in this case. Okay. And another example. A is a set of x where x squared is equal to 1. And B is a set of -1 and 1. So in this case, this set A is actually the solution of x squared equal to this equation, x squared equal to 1, which is actually -1 and +1. So these two sets are actually equal. So every set of A, -1 and 1, is an element of B. So and vice versa, every element of B is an element of A. So these two sets are equal. In mathematics, it is usually a source of trouble if we consider the set of everything. I mean, literally everything is actually quite useless because it can cause some contradictions, as we will see in the next lecture, perhaps. So we usually fix our universe of interest. Let's say we call that as the universal set. Okay, universal set. Maybe we should write that here. The universal set. This is the set of everything we are interested in. Okay, of everything we are interested in. So this part is important, that we are interested in. Okay, without this, the set of everything is it's a source of trouble, because if we consider the set of everything, then it should include the set that does not include anything, or and also it should include the set of everything. So the set itself is a member of itself. So it's a kind of source of contradiction, and it does cause a contradiction. So we exclude that possibility by limiting our interest. Okay, so say the set U is the universal set. Universal. Then when we specify a set, we write like this: x belongs to U, and x has some property. like this. So we do not consider literally everything, but we fix our attention to this set. Within this set, we consider what we are trying to study. Okay. Now we define union and intersection of sets. Union. So let's say A and B are sets, then their union is defined as this. X, where X cup B, that's how we pronounce this. This is a union between A and B, which is a set of elements that belong to A or B. Okay, so this is the property here. It's a logical statement. So this means every element of A cup B belongs to either A or B. Of course, it can belong to both of these, if that's possible. And similarly, we define the intersection between A and B, which we write like A cap B. So this is cup. This is cap. This is the set of elements that belong to A and B. Okay, so this means this every element of this must belong to both A and B. Okay, so this is these are the definitions of union and intersection, and we can extend this to many sets, like the unions of A cup, B cup, C. So this is the union of three sets. So this can continue to many sets. And similarly, intersection can be extended to many sets, and so on. And if we have a sequence of sets like A1, A2, A3, and so on, we may write the union like A1 cup, A2 cup, A3 cup, and so on as this: cup, n from 1 to infinity, A n. Of course, if it's not infinite, then, for example, A1 cup, A2 cup, and so on up to an, for example, then we can write like from this index a, n, or k. In this case, they are just variables, so we can choose any letters. So we may write like this. So this is like just like summation of a sequence. So from I from 1 to n. Similar to this summation, we can write like cup. And similarly, we can write the intersection of indexed sets like this as cap, k from 1 to n, ak, like this. Now let's prove a little lemma. So let's say A, B, X are sets, and assume A is a subset of B. Okay, then we have the following properties. Okay. A intersection X, so A cap X is a subset of B cap X. And 2, A cup X is a subset of B cup X. Okay, so let's prove this. First one. So according to the definition of the subset, what we need to prove for this one is to show that if X is an element of a cap X, then X is an element of B cap X. Right? So if we can show this, then we have proved this one. So let's assume this, okay? So assume X is an element of A cap X. Then if that's the case, we have, first of all, our assumption is this. A is a subset of B. Okay, so let's see. X is an element of A cap X, so this means X is an element of X and X is an element of X, right? So that's the definition of intersection. But since we have this, we have X is an element of B. And of course, this still holds. But this is actually a definition of B cap X. So X belongs to both B and X. So therefore, this X is an element of B cap X. So that's what we wanted to prove. So the proof is done here. And for the second part, suppose X belongs to a cup X. Then this means X belongs to A or X belongs to X. That's the definition of union. Okay. But since if X belongs to A, then this means X belongs to B because of the assumption here. This assumption. Assumption is A is a subset of B. Then this or this means X belongs to B cup X. Definition of union. Okay, so therefore we just proved what we wanted to prove, and the proof is done. Next, we define the complement of a set. Complement. Okay, let's say A is a set and U is a universal set. Universal. So that means anything we are dealing with belongs to this set U. Okay, then the complement A prime, or we write AC, that's the complement of A, is the element which we write A prime is the element of X. Of course, this is an element of U such that X does not belong to A. Okay, so we also write this as this, or we write like U backslash A. So these three notations mean the same thing. Okay, so if this is the universal set U, and if this is A, then A complement of A is everything outside of A. Okay, so we do not consider outside of U because that's the universal set. Okay, so that's the definition of complement. And you should also note that the complement of U itself is empty because there's nothing outside of U. Okay? So if we go back to the definition of this complement, then complement of U should be the element of U that is not an element of U. But so this means X is an element of U and X is not an element of U, which is a contradiction. So no element can satisfy both of these at the same time, so it should be empty. Okay. And also there are some equalities involving universal set U, so that's complement of A and union A. So that should be so everything within A and everything outside of A. If we take the union of these, it should be the universal set. And also, if we take the intersection between these two sets, we sometimes call it U minus A, cap A. So this should be empty, right? Because nothing is common between these two sets. And related to the complement, we can also define relative complement or set difference. Or set difference. So suppose we have two sets, A and B. The relative complement of A with respect to B is written as this. This is the subset of B that is not part of A. Okay, so this is the relative complement of A with respect to B. Okay, so suppose we have the universal set and we have the set A and we have the set B. So this is we call it B minus A, is everything within B that is not in A. So that would be this part. Okay, so this part would be A B minus A. So that's the relative complement. Now let's prove a theorem. Suppose we have two sets, A and B. Okay, they are sets. Then the following statements are equivalent. So A is a subset of B, and A cap B is equal to A, and 3 A cup B is equal to B. So these are equivalent. So what this means is that if this holds, then this and this are also true, and vice versa. If 2 is true, then the other two statements are true, and if 3 is true, then other two statements are true. So to prove this, what we need to do is to show that if 1 is true, then 2 is true, vice versa. And if 2 is true, then 3 is true, and vice versa, and so on. We can prove in any order actually. So we can prove if A is true, then 3 is true, and so on. It can be proved in any order. Okay. Let's try to prove this. Okay, let's prove this. First, we try to prove if 1 is true, then 2 is true. So to do so, let's say we first suppose A is a subset of B. Okay, so this means if X is an element of A, then X is an element of B. Okay, because that's the definition of a subset. Now, what we want to show is these two sets A cap B is equal to A. So to show that, we need to prove two things. So if X is an element of A cap B, then it is also an element of A. And if X is an element of A, then it is an element of A cap B. So to show this, to show A cap B is equal to A, we need to show this A cap B is a subset of A, and A is a subset of A cap B. So if both of these holds, then we say these two sets are equal. Okay. So far we have this result. Okay. And let's see. Let's show this one first. So if X is an element of A, then from this, then X is an element of B by this. Therefore, X is an element of A, and X is an element of B. Therefore, X is an element of A cap B by the definition of intersection. Therefore, A is a subset of A cap B. Okay, so this one has been proved. Now prove this one. X is an element of A cap B, then X is an element of A, and X is an element of B. So we have, if this is true, then this is true. And in addition, this is true, but in this case, it's not so relevant. Therefore, A cap B is a subset of A. So we have this, we have this. Therefore, A is equal to A cap B. So by assuming A is a subset of B, we have proved A is actually equal to A cap B. Okay. Now let's prove the converse. Okay. If 2 is true, then 1 is true. Then to prove that, so 2 is this one. Okay. So suppose A cap B is equal to A. Okay, then we need to show that A is a subset of B. Okay, let's see. So this means X is an element of A and X is an element of B is equivalent to X is an element of A. So this means if X is an element of A, then X is an element of B. So this means A is a subset of B. And we are done. And the other thing, equivalence, like this equivalent to this or this, can be proved in a similar manner. So I will skip it. So that will be an exercise. Next, we define the Cartesian product between two sets or more. Suppose A and B are sets, then the Cartesian product between A and B is written like A times B, which is the set of pairs of elements such that the first pair the first element of the pair is an element of A, and the second element of the pair, component of the pair, is an element of B. Okay. For example, let's say A is a set of 1 and 2, and B is a set of 2 and 3. Okay, then in that case, A times B, the Cartesian product between A and B, is the set of all pairs of which the first component is an element of A and the second component is an element of B. So that would be 1, 2, 1, 3, and 2, 2, and 2, 3. Like this. So in general, we in case of finite sets, if A and B are finite, then the cardinality of A times B is the product of the cardinalities of A and B. Okay. In this case, there are two sets in A, two elements in A and two elements in B. So the number of elements in A times B is 4. that is 2 times 2. And this Cartesian product can be extended to any number of sets. So if we have A1, A2, A3 up to AN. So all these are sets. Okay, so we can define A times A1 times A2 times and so on times AN, which is the set of ordered tuples. So A1, A2, AN, where A1 belongs to the set A1, A2 belongs to set A2, and so on. Next, I'm going to list a series of theorems without proofs, and the proofs are left as exercises. Okay, first, you can prove those in using Venn diagrams. The first is this: A cup B complement is A cup cap A complement cap B complement. This is one of the De Morgan's law, and also A cap B complement is A complement cup B complement. Okay. Of course, A and B are any sets. And next, distributive laws. A cap B cup C is A cap B cup A cap C. Okay. So this is like if we have B and C. So if we have this, so this is B cup C, right there. This is the union. And if we have A here, if we have a cap, then that will be this part. Okay, so this part can be also expressed as this union this, right? So A, let's see, this is A, and A cap B is this part, and A cap C is this part. And if you take the union, it will be the same area as this. Okay, and similarly, we have A cup B cap C is equal to A cup B cap A cup C. Okay, and what else? Okay. What about cardinality of A is A minus B cardinality plus the cardinality of A cap B. This should be trivial from the definitions of set difference. And using this relation, you can also prove that the cardinality of A cup B is equal to the cardinality of A plus the cardinality of B minus the cardinality of A cap B. If we extend this, then the cardinality of a cup B cup C, the union of three sets, is equal to this. So A plus B plus C minus A and B minus A and C minus B and C plus A and B and C. Okay. And yeah, that's about it, I think.